Welcome to the critical line, where mathematics, geometry, and entropy converge to illuminate one of the most elusive problems in human thought, the Riemann hypothesis. I'm Greg, and today I'm joined by Andrew, one of the researchers behind a newly proposed proof. Andrew, it's an honor to have you here. I'll pass it over to you in a second, Andrew, to introduce yourself. Following your introduction, I have so many questions for you. Firstly, to set the stage, what is the Riemann hypothesis, and why is it such a big deal? And secondly, your approach doesn't rely on the zeta function directly. Can you explain that in detail?
Thanks, Greg. It's a privilege to be here. We believe we've discovered a fundamentally new approach to understanding identity, entropy, and number theory, without relying on traditional formulations of the zeta function. Firstly, let's talk a little bit about the Riemann hypothesis. The Riemann hypothesis is a mathematical conjecture about the 0 points of a special function called the Riemann zeta function. This function accepts complex numbers as input, numbers that have both a real and an imaginary part. The hypothesis states that all of the nontrivial 0 points, where the function evaluates to 0, lie on a specific vertical line when plotted on a complex plane. That line is where the real part of the input equals 1/2. And it's an important function because the 0 points of the function turn out to be deeply connected to how prime numbers, like 2, 3, 5, 7, are distributed. If we know where these zeros lie, we gain powerful insight into the structure and predictability of prime numbers. And since prime numbers are fundamental to number theory, cryptography, and even physics, solving the Riemann hypothesis has massive implications. And so this brings us to your second question about my approach for solving this conundrum without relying on the zeta function. What we see is that traditional approaches focus on analyzing the behavior of the zeta function through infinite series or complex analysis. But I, along with colleagues, flipped the problem. Instead of starting with the function and looking for where it goes to 0, we built a geometric and symbolic framework that predicts where those 0 points must occur. We call this framework the entropy spiral.
Andrew, that's fantastic. I'd love the audience to understand what you mean about the entropy spiral. We know that in physics, entropy is a measure of disorder. What does it mean in your work? Moreover, I know that you're taking a geometric and physics-based approach for solving the Riemann hypothesis. For the audience, I'd also like you to talk about torsion, curvature, and collapse points, and how they correspond to the zeta zeros.
Yes, Greg. That's right, entropy typically measures disorder. But in our theory, entropy is redefined as a symbolic energy, a structured field that reflects how information resists or succumbs to symmetry. Identity, in this context, means the emergent stability of a system's self-definition. When entropy collapses, when disorder becomes minimized, a system can crystallize its internal order. That moment is when identity becomes robust and meaningful. And so in this case, identity is the stable fingerprint of structure after all degrees of freedom that would cause distortion have vanished. In our model, this happens at collapse points where entropy reaches a minimum. These points are where curvature and torsion cancel out completely. In terms of torsion, curvature, and collapse points. Curvature is how much a structure bends in space. Think of it as a geometric memory of deviation from flatness. Torsion refers to twisting, the way one part of a curve turns around another. In our symbolic manifold, we model the evolution of structure as curves through information space. Where these curves flatten and untwist, 0 curvature, 0 torsion, we find what we call torsion minima. Those are collapse points. And so, the nontrivial zeros lie exactly at these collapse points. That's the key. These aren't abstract outputs of a function, they are structurally inevitable consequences of entropy geometry. These collapse points are the geometric loci that encode the prime distribution indirectly. Each collapse point maps to a prime resonance in the underlying informational field.
This is really fascinating, Andrew. That's very different from traditional mathematics. But how do you formalize all this into something rigorous? Also, how does your theory satisfy the Hilbert-Polya conjecture, the trace formula, and the Hadamard product? What are the implications for the future of mathematics based on this discovery?
In terms of rigor, we developed 67 axioms, symbolic laws of how structure, entropy, and identity behave. From these axioms, we construct an operator, a symbolic projection kernel, that acts on entropic manifolds. This kernel behaves exactly like a self-adjoint operator, which is what the Hilbert-Polya conjecture called for. How do we address the Hilbert-Polya conjecture? The Hilbert-Polya conjecture proposes that the nontrivial zeros of the zeta function correspond to the eigenvalues of a yet unknown self-adjoint operator. Our operator, derived from entropy collapse dynamics, generates eigenvalues that match the imaginary components of the zeros. This isn't just numerically convenient. It means we've built a structure that must yield those values by design. The symbolic projection kernel embeds geometric and entropic constraints such that these eigenvalues are necessary outcomes. As far as the trace formula is concerned, the trace formula in physics connects periodic orbits in classical systems with quantum energy levels. It essentially says that quantum behavior arises from classical periodic structures. In our entropy spiral, we discover similar periodic geometric resonances, closed loops where entropy collapses symmetrically. When we trace over these resonance zones, we recover the exact imaginary values of the zeta zeros. These loops form constructive interference patterns in the symbolic field. When traced, their total resonance energy matches the zero distribution. This proves that our geometry isn't just suggestive, it's functionally equivalent to the classical trace structure required in analytic number theory. What's interesting from all of this is the Hadamard product reconstructs the zeta function from its zeros. When we substitute the zeros derived from our collapse geometry, we recover the classical behavior of the zeta function, logarithmic divergence, Euler product properties, and all. The accuracy is not coincidental. These zeros are born from structure, so their synthesis into the function is natural, and we walk through this in our very long proof of the Riemann hypothesis. It suggests that the zeta function is emergent from this discovery. In terms of future application, first, we now know that prime distribution is not random, it's governed by entropy geometry. Second, the framework bridges math and physics through identity emergence, showing that systems, from primes to particles, stabilize at entropy minima. Third, this gives us a symbolic map of number theory, not unlike a DNA code for structure. We see this impacting quantum computing, particle physics, even consciousness studies. Wherever structure emerges from disorder, this theory could apply. It rewrites how we model systems, not with equations alone, but with symbolic collapse fields. That's the future.
Andrew, thank you. This was one of the most insightful conversations we've ever had. This has been The Critical Line. Until next time, stay curious and stay structured.